Here's your first Camtasia video. What I'm about to do is pretty much what I do in my land-based class. So about every time or when I have lectures, this is pretty much what, like I said, what I do. So I think it really would be to your advantage if you look at these first before you go and look at the videos in the book. The textbook, use that as a backup. I do some things a little bit differently, which I think they're a little bit more efficient. But you need to try, since this is a web-based class, you need to use as many of the resources that you've got, okay, including the tutors, you know, anything, even online, because the my math lab also has tutors. But let's go ahead and get going on this. This is our very first section. This is Introduction to Limits, and this is something that we have to do because it's part of calculus. Now, usually the evaluation of a function at a point is straightforward. That is, the value of this function at x equals 1. I can write it in functional notation, f of 1. This means for me to substitute 1 in for x wherever I see it. And if I do that, I end up with 3 in the numerator, 2 in the denominator. So now this is just how we evaluate a function. However, there are situations when it is not so obvious and special measures are needed. The difficulties can be roughly divided into two categories. Division by zero, that is, what is the behavior of this function near x equals 1. If you'll notice, if I substitute 1 in, we have issues. Also, how does this function behave when x goes to positive or negative infinity? If you remember from pre-calc, this deals with asymptotes, but we do this one a little bit later. The answer in these cases is to keep track of the values of f of x. Remember, f of x and y are the same. So keep track of those y values as x approaches the required value gradually. There is a hidden simplicity, and I want to start with an example that's not as complicated as it first appears. How does this function behave near x equals 1? Well, the problem is that if I do direct substitution, I end up with 0 over 0, which, as we know up to this point in time, is undefined. Now, in calculus, we call this 0 over 0 an indeterminate form, and it does tell us something. If we do a little bit of algebra, factoring, it exposes the answer. Factor the numerator, and I have this. If you'll notice, I've got x minus 1 in common. And if you cancel like factors, I end up with x plus 3. So you see, I can reduce this function down to x plus 3. Now, I graphed the original because I wanted you to see what it looked like. I've turned it on. This one's turned off right now. But if I graph that, now also I had to modify the window. At Zoom 6, the standard window, you couldn't see what I'm about to show you. The window I used was my x value min from 0 to x max of 2, scale is 1, y min 3, y max 5. And if I ask it to graph, that's the issue. This is why I cannot do direct substitution. But there's another thing I need you to see here. If I do my x values gradually as I get close to an x value of 1, I do have y values until here, that hole. Also coming from the right, same issue. It looks like as my x values get closer to 1, my y values get closer to 4. And in fact, if you substitute 1 into the reduced function, notice I do end up with 4. Alright. So the question is, what is the value of f of 1? As x approaches 1, the reduced function f of x equals x plus 3 is valid. So f of x approaches the value of 4 because I can do direct substitution. We can reassure ourselves of this by calculating the original function when x is approaching the value 1 from both sides in the following table. But now I wanted to show you one more thing, and this is why I had the other one turned off. Let me go turn it on. Now I need you to blink because you'll miss what's about to happen. You ready? Now I need you to remember where the hole is. Look at the hole. It filled it up. It's the exact same function, yet it exists everywhere. So now I need to go back to y equals. Let me clear this one, because I'm going to show you how to do a table using this graph. Now I need to move this down a little bit more. So I'm looking at these values. Now I could substitute these values in one at a time, but it would take me a little bit of time. What I'd rather do is use the graph. It's a whole lot quicker. Once you have the y equals, put it in, type it into y equals, use your parentheses. Let me go back to Zoom 6. Now, I use the calc menu a lot. You need to get used to it. So I'm going to do second trace for the calc menu, and I want number 1, value. Let me hit enter. And it's going to prompt me for an X. Now I'm going to, if you'll notice, here's some notation right here. Do you see the negative after the 1? That's telling someone who understands this notation that I'm approaching 1 from the negative side, or coming in from the left. If you'll notice, I've got a plus here, so that means I'm approaching 1 from the positive side, or coming in from the right. So let me type in 0.9. So 0.9, hit enter, and it's actually going to give me the coordinate point and where it is. And if you'll notice, there's my y value. Let me type in 0.99. So you see I'm gradually get closer and closer to 1, and as I do, I'm getting closer and closer to a y value of 4. Let me type in 0.999. Hit enter. So there's that value. Notice it's very quick. I'm letting the calculator do the substitution. Let me come in from the right hand side. Let me start at 1.1. There's my 4.1 value. Let me try 1.01. There's my 4.01. 1.001. So I can safely say that as x is approaching 1, coming in from the left and from the right, my y value is approaching 4. This takes a little bit of time to me. I'm a math major. I like to factor. Factoring, I think, is the quickest way to go. Alright, so definition of a limit. We now need to introduce some notation in order to be able to express the idea more concisely, or in mathematical form. Rather than say let x approach the value of a, we will write this: x with an arrow. The arrow is indicating approaching a. Approaching does not mean I get there. Now if f of x approaches a number called L as x approaches a, then we say that the limit of the function as x approaches a is equal to this number, and we write it as limit of my function as x approaches a is equal to L. So this is the mathematical notation for that word expression. This means that we can make the value of f of x as close to L as we like by taking x to be sufficiently close to but not equal to a. And we can write the previous example, the one I had a little bit earlier, as this. So here's my function. There's the reduced form. So the limit of my function as x approaches 1. I couldn't substitute it in here, but I can here. It equals 4. Now I know I'm saying substitution, but guys, if the value exists, that's the quickest way for me to tell you what I'm getting closer and closer to. Now the existence of a limit. In order for a limit to exist, the limit from the left and the limit from the right must exist, and they have to be equal. So my notation here is the limit of f of x as x approaches a from the left, from the negative side, is equal to this value. The limit of my function as x approaches a coming in from the right, or the positive side, is equal to this function. Now, if no direction is specified, direction meaning the little negative behind or positive behind in a limit statement, you assume that the limit is two-sided or unrestricted, which means I have to do both of them. And in order for me to have an answer, then these values here, this L, has got to be the same. Now I do need you to go to page 478. Look at that example. There are properties I need you to look at on page 480. Okay, that's the end of this particular video, and there will be more to follow. Thank you.